Hello, everyone. My name is Larry Rizzolo. Welcome to another lecture from the Chautauqua Science Circle. And today, this is a re-recording of an earlier talk to correct some of the sound issues, some of the technical issues. I'd like to introduce Paul Nordine, who received his PhD in chemistry from Kansas University in 1970. He became an associate professor of chemical engineering at Yale in the 1970s, then switched to be a research scientist at Midwest Research Incorporated in Kansas City during the 80s. And since then, he's been in R&D and administration at scientist-owned R&D companies in Evanston, Illinois. Up until 2012, he's now retired. Living with his wife, Justine, who happened to be a former Chautauqua B&B owner. And they live together now at 9 Simpson for half the year from June until December. Paul's talk will be why does carbon influence the Earth's climate? And so I give you Paul Nordine.
Okay, thanks, Larry, for the introduction. You know, a lot of scientists are studying the consequences of global warming. But this talk is going to be about not the consequences, but the cause, which is atmospheric chemistry problem. And in fact, my PhD is in physical chemistry, which is the right discipline for studying atmospheric chemistry problems. So although this has not been my career, it's been my intriguing interest now for several years. And I want to talk today about what I've learned about the cause of global warming, or how carbon dioxide influences the climate. This first slide says, is to explain how much excess energy the Earth does receive. And the 2013 excess was said to be about 2.2 watts per square meter by the fifth assessment of these issues by the International Panel on Climate Change, a very large organization that has most of the scientists that studied these effects contributing. Now, if you multiply that 2-watt light bulb per every square meter by the number of square meters that the Earth has, you end up with 1.2 billion megawatts. You can compare that with the total U.S. electrical unit utility capacity, which is only 1,000, which is 1,000 times smaller than that excess heating of the Earth that the effect of carbon dioxide and other chemicals in the atmosphere produce. So it's important to understand how it is that comes about, how it is that the chemistry of the Earth's atmosphere influences the warming effect. This one right here. So I'll go on to the next slide. Now, how do I get back? Right there.
You're right.
This slide shows some of the sources that I've used for anybody that might be interested in the subject. And although this talk was given in the second week, it's now the 6th week, and the new 2011 IPCC report has come out. The very last reference is to that report I've added to the talk. So if you want to see the very latest thing, you can find the 4,000-page report by the IPCC in that last reference. The talk I want to give now, if I can get my slides right, is this story that has several different parts to it. First, I want to speak about the scientists that have figured out how the atmosphere influences warming, and then how solar heating by the sun is balanced by the emission of infrared radiation that goes back to space. Now, visible sunlight comes in, or near visible sunlight comes in, but infrared radiation is what goes back out because the Earth is so much colder than the sun that it doesn't emit visible light. It emits infrared light. As it turns out, that problem involves understanding a little bit the structure of the atmosphere and the way in which carbon dioxide absorbs that radiation and then re-emits it. So the fifth part of this talk will be about the altitudes in the atmosphere, given its structure, at which the infrared is in fact emitted to space. It doesn't all get emitted from ground level. And finally, I want to finish the talk by saying a few things about ocean heating and the effects of clouds. Here are the earliest scientists that contributed to this problem. In 1896, Arrhenius wrote a paper on the influence of carbonic acid, as CO2, carbon dioxide was called in those days in the literature, and on the temperature on the ground. And he predicted that increasing carbon dioxide would, in fact, affect the temperature of the Earth. At that time, however, there had not been a sufficiently large increase from pre-industrial times that was a measurable problem, but it was one that could be predicted if the carbon dioxide continued to increase. There was quite a bit of controversy over Arrhenius's ideas, but they were eventually accepted after some objected and others supported his ideas. And in 1956, Gilbert Ploss wrote the first really analytical analysis of how carbon dioxide does influence emission of Earth's emission of infrared to space. His model was a fairly simple one, but it certainly proved that there's something, it showed how to approach the problem. And when good computers came along, it became possible to analyze that problem much more exactly than he could have. So now skip forward to 94. 1994 is when Sir John Houghton in England published his first paper on global warming. His first book on global warming that described the ideas that had been developed up to that time. His book is now in its 5th edition, and you can go through those editions and see how much progress has been made in the years since 94 to the latest edition, which was a few years ago. Unfortunately, John Houghton, who was a major contributor to this, died this past year. In fact, it's reported in the literature from the virus that we've just suffered through, or haven't quite suffered through yet. These two authors were at the University of Chicago when they wrote the books that I mentioned next. David Archer and Raymond Pierre Humbert are major contributors to the field, as well as books that are very useful in understanding what that field contains. The book that the two authored is called The Warming Papers. It has all of the significant papers, including the 1896 paper and others, and even papers earlier describing the properties of carbon dioxide that by 1896 were understandable. The other book is by Pierre Humbert alone on all of the planet's atmospheres and how they are influenced by the atmospheric chemistry. These two persons are John Houghton again and Al Gore, who I want to mention because they are the men mentioned in the 2007 Nobel Peace Prize Awards. I didn't know this until I looked it up, but Al Gore, as a freshman member of Congress, was in the business of conducting hearings on climate change as early as 1976. So given the fact that he was certainly one of the movers in this world, who was earlier than almost anybody else, or certainly earlier than the scientists, I would say, except for Ploss, one has to conclude that he well deserved the Nobel Prize that he was granted. John Houghton was the man mentioned as a leader of the other organization that shared the prize with Gore, and that is the International Panel on Climate Change, which I've mentioned earlier in their recent 4,000-page report. There's one other person, scientist, that I want to mention here, and this is a woman. It's Joanna Haig, now retired from Imperial College London. And the reason that I want to mention her is because her book with Zong on the greenhouse effect in carbon dioxide is one that I make a lot of uses of in this talk. That completes the talk about the scientists. And now let's turn to the way in which carbon dioxide influences heating of the Earth. The concept that is generally employed is called radiative forcing. What's done is one calculates the difference in the amount of infrared radiation that passes through the tropopause going upward and coming back downward. And if there's more coming back down now than there was in 1750 in the pre-industrial area when carbon dioxide was stable in the atmosphere, then the amount of radiative forcing is equal to that difference. As of 2013, that was calculated to be a value of 2.29 watts per square meter, that value that I used earlier in calculating that enormous input that the entire Earth thus receives. But it's a relatively uncertain value, as you can see in this bold-faced print near the bottom of the slide. The range of estimation is from 1.1 to 3.3 values, with 2.29 selected as the most probable value. Now, there's other information that suggests that that value is most probably a better estimate than the range of uncertainty indicates. But the calculations themselves have that kind of an uncertainty. I'll get to that. This is what the infrared spectrum looks like as measured as long ago as 1970 by two NASA scientists, Hanel and Conrath. You can see to the left side of the upper figure, there's a very large dip in the emission spectrum where carbon dioxide absorbs infrared radiation. Otherwise, the spectrum rises and then falls as you go through the wavelength range of light or of infrared that the Earth emits. You can also see that there's a small dip where ozone in the stratosphere absorbs some of the light. And there's a further dip further out where methane and water have additional absorption effects. If you look over the Sahara, desert, as Hanel and Conrath did, you see that there's more emission than there is over the Mediterranean, where the Earth is cooler. There's also a smaller dip in it due to the carbon dioxide because there's less emitted in the first place. But the dip gets just as low as it did as it does in the Sahara. But now, if you go to the Antarctic, where it is extremely cold at the surface, the region where carbon dioxide absorbs infrared actually emits more light to space than would the surface if the carbon dioxide wasn't there. And furthermore, that also occurs, if you look carefully, in the ozone absorption. The ozone also emits a little bit more. There's a very small bump there where ozone absorbs infrared radiation. And that is a clear indication that the stratosphere is important in this whole business because ozone exists mainly in the stratosphere. So that was when I saw that, that's what really intrigued me to look at the idea of how the atmosphere structure influences this whole business. One needs, therefore, to look at how that structure is arranged. And there's three major parts of the atmosphere that are involved here. The troposphere, which is where all the weather and clouds are, or most of the clouds and much of the weather is a region where the temperature decreases with altitude for the first 10 or 15 kilometers of altitude. These are temperature Kelvin. You got to add 270, you have to subtract 273 to get it in Celsius. So the top is a little bit above 0 Celsius, and it gets down to about 50 degrees below Celsius according to this US standard atmosphere. In the stratosphere, however, the temperature increases with altitude. And the reason for that is that the stratosphere is where ultraviolet radiation from the sun is absorbed by the atmosphere and to heat it. If it weren't for that effect, we'd be seeing too much ultraviolet radiation, and that would not be good for sunburn and skin cancer, for example. Above the stratosphere, which ends at about 50 kilometers altitude, the temperature begins to decrease again, and that's the region called the mesosphere. Now, all three of these areas are ones in which carbon dioxide can absorb light somewhere within the absorption spectrum that is found. And I'll get to that point in subsequent slides. This slide I've included, it's NOAA data that illustrates how the temperature structure of the atmosphere varies throughout the year. This is for the year 2020. For a region, it's sort of an average for regions in the 60 to 90 latitude, 60 to 90 degree latitude regime. If you look in the summer at the center of the thing, you can see that there's a large green area there in the middle, which is that bottom point where the tropopause, where the troposphere ends and the stratosphere begins. But in the wintertime, on the left in January or on the right in December, you can see that there's a considerable change in the structure of the atmosphere that can occur. The gradients are different than they are during the summer, and the temperature becomes a minimum at a significantly higher latitude than it does in the summer. So taking that into account, rather than just using the standard atmosphere, is necessary when one has to make very accurate calculations of the effect that carbon dioxide can have. And it's for that reason that there is some uncertainty in the value of the calculations, because the ability to take that completely into account makes the calculations even more difficult. This is the same figure, but in the equatorial region, the region between -10 and +10 latitudes. And here you can see that the structure of the atmosphere throughout the year doesn't change very much. But one thing that's quite interesting about it is that the white area, which is the tropopause area, is much colder than it is at the northern latitudes. In other words, in the cold part of the world, the tropopause is warmer than it is in the hot part of the world. Well, that's understood by climate scientists. But in fact, the tropopause is much colder than the standard atmosphere at this point. And so that is something that needs to be taken into account in the analyses. And it's this variation of the structure of the atmosphere with time and latitude, time of the year and latitude, that makes it more difficult to get real accurate results. At least that's one of the problems. So that ends what I have to say about the structure of the atmosphere, and the question then becomes, at what latitude or altitude is the infrared emitted to space? Is it emitted in the stratosphere, or is it emitted in the troposphere or mesosphere? How much is in either area? Now, why is it interesting to know that? It's because in the stratosphere, if you add more carbon dioxide, one has to go to a higher altitude before the light can escape to space. More carbon dioxide will absorb it more effectively. So that light, that infrared, which is being emitted in the stratosphere, will move to a higher altitude where it is warmer. And being warmer, there will be more emission that escapes to space. So emission from the stratosphere is actually a cooling effect. More emission from the stratosphere will cool the Earth. Now, in the troposphere and the mesosphere, it's just the opposite. The temperature decreases with altitude, So increasing the carbon dioxide will cause emission to space at a higher altitude, and therefore lower amounts, and it's a heating effect because there's less cooling. Now, in order to know how the infrared is emitted to space, one has to look at the absorption coefficient of carbon dioxide, which can vary over a very large range. And this is a figure which shows that effect. It's from the paper by Zong and Haig, which I've made good use of. The upper curve shows the absorption coefficient spectrum of both carbon dioxide and water. Now, water is present mainly in the troposphere. It doesn't change much from time to time. It's not really a big concern in trying to figure out the difference between pre-industrial and current times. But carbon dioxide, which is mixed quite uniformly throughout the atmosphere, is really important in doing that because it's now quite a bit more concentrated than it was in pre-industrial times. If you look down at the emission spectrum, you can see that the absorption by carbon dioxide appears at a wavelength where the absorption coefficient of carbon dioxide, the red curve, is 0.01 in these units. And if you look at the center of the absorption spectrum, there, the absorption coefficient of carbon dioxide has a value of 10,000 of these units. Now, the units are meters squared per kilogram of carbon dioxide. That makes sense, doesn't it? Because meter squared is sort of like the size of an area that 1 kilogram would provide as the target for the infrared radiation. Water has a small influence on this, has a significant influence on the spectrum. If you look at the lower figure in this slide, there's a red line that says what would be observed if the atmosphere were completely transparent. That's what the Earth would emit if nothing were absorbing some of the radiation. So in the region where water has a large value, there's a decrease in the emission from the red line, both at shorter parts of smaller wave numbers and at larger wave numbers. And that's indicated by the H2O figures that are put onto the graph. Now we can address this question about where infrared is emitted to space. The carbon dioxide absorption coefficient, as we saw, has units of meter squared per kilogram, an area per unit mass. Now we know, most of us know, the atmospheric pressure, like tire pressure, is measured in pounds per square inch in English units. And pounds are equivalent to kilograms, or they're like kilograms, and square inches are like square meters. So the units of atmospheric pressure are just the opposite of the units for the CO2 absorption coefficient. And if you multiplied the atmospheric pressure in kilograms per square meter by the amount of carbon dioxide there is, you would have the number of kilograms per square meter in the atmosphere above the point at which the pressure is the value that you used. And that's what that is the amount of kilograms per square meter that remain in the vertical direction. So if the amount of kilograms per square meter of carbon dioxide that remains in the vertical direction is comparable to the reciprocal of the absorption coefficient, that identifies the pressure at which emitted radiation of that wavelength, the wavelength that corresponds to that absorption coefficient, can be emitted. Now, to consider that insight, I've expanded the absorption coefficient spectrum that was shown in the paper by Zong and Haig to get this figure here. Now we only show the spectrum over the range where carbon dioxide absorbs. And you can see that it's comprised of a large number of sharp peaks followed by wider valleys between the peaks by this inset that's shown there. The reason I've done that is you can see that the peaks are much more narrow than the space between them. And so the absorption coefficient values in the valleys down below are far more important than the values in the peaks in controlling emission to space, because they just cover a larger part of the spectrum. So if we look at this region here, where the valleys are in the stratosphere, but the peaks are in the mesosphere, still the stratosphere will be have the principal control over emission to space. Although a little bit of it will be coming from the mesosphere due to the peaks in the absorption spectrum. Furthermore, it's where the valleys in the spectrum, the bottom part of the spectrum, crosses from one part of the atmosphere to the next, from the stratosphere to the troposphere, for example, where the switch will occur. That's where the tropopause is going to be. Below that point where they cross, the emission is going to be controlled by the troposphere, and above it, it's going to be controlled by the stratosphere. So you see, the central part of the carbon dioxide emission spectrum to space comes from the stratosphere, and it's a cooling effect, whereas the wings of the carbon dioxide emission come from the troposphere, and that's a heating effect. And if you just looked at this, you might say, wow, the troposphere isn't very important, but it turns out that it is very important. And the net result is the troposphere dominates the stratosphere in the effect that it produces. That was analyzed with some care by Zhang and Haig, and this next slide shows what their result was. In this slide is given the change that occurs in emission to space as a function of the wavelength over that same range of wavelengths where carbon dioxide absorbs. If one changed the concentration of carbon dioxide by a factor of 2, they did these calculations as of 2011 when there was 387 ppm, so the change was to 774, twice that. You see there's more emission to space, it's positive, in the center of the spectrum, and there's less emission in the wings of the spectrum. And you can also see that the wings comprise a larger area than the center. So that means that the wings of the spectrum are more important in the global heating problem than the center. In other words, we get heating instead of cooling. I can compare this plot with the one previously shown when the lines across that are recalculated for the 387 to 774 range. What happens is that if the concentration is 387 parts per million, the red lines show where the mesosphere emission begins. If you double it to 770, or the stratosphere or the ground level emission begins. If you double it to 774, those lines move down. That means you have to get to the mesosphere to emit if there's more CO2. You have to get from the troposphere into the stratosphere to emit if there's more CO2. And furthermore, the ground emission can occur at larger and smaller wavelengths. In other words, the spectrum itself is broadened if you increase the concentration. And it's very much largely the broadening of the spectrum that is responsible for the increased heating that exceeds the increased cooling that the stratosphere would produce. At the bottom of here, you can see the spectrum superimposed on that drawing that Zhang and Haig obtained. And you can see that the transition from a heating effect in the stratosphere to a cooling effect in the troposphere is just about the place where the bottom of these lines cross over those lines. So that confirms that that simple analysis of calculating these lines that define the regions of the atmosphere, that simple analysis is approximately correct. When the pressure multiplied by the concentration of carbon dioxide in the atmosphere equals the reciprocal of the absorption coefficient. That's the point that determines the pressure at which at which infrared radiation, the nominal pressure where infrared radiation can escape to space. That pretty much concludes what I have to say about that part of the thing, and I want to just make one more comment that derives from Zhang and Haig's results. They analyzed this problem from 0 to very large, 2,000 parts per million, and that black curve shows what they obtained. Now, if there is no carbon dioxide in the atmosphere, there's a very big difference in the so-called radiative forcing effect. It's like minus 30 or 40 watts per square centimeter. So if that were the case, the Earth would be emitting a lot more infrared radiation, which means that it would be cooled by the absence of carbon dioxide. And if there were no CO2, the average temperature of the Earth would be about 39 Fahrenheit instead of around 60 Fahrenheit, which it is today. So one can say we're awfully lucky that there's a lot of CO2 in the atmosphere, because it would be freezing most of the time in much of the world if it weren't. On the other hand, you can see what Zhang and Haig have here. 280 parts per million is what we had in pre-industrial times. So it was already a warm Earth by those days, in the first couple centuries of recorded time were nice and warm. But there was a slightly negative value relative to 2011, which was their 0 point. Now at 410 ppm, it's about 2.6 watts per square centimeter larger. Let me say it this way. At 280 ppm, their calculation gave minus 2.6 watts per square centimeter relative to 2011. But now in 2020, we have 410 ppm parts per million, and that gives us 0.2. So the difference is about 2.8 watts per square centimeter. Zhang and Haig's results are pretty close to what the IPCC was predicting. That's one of the things that I would cite in saying the IPCC selection is probably believable, at least. One doesn't have to think it's quite as uncertain as they suppose. Let me turn now to the ocean and the clouds, which will finish this talk. NOAA has measured the temperature of the ocean since the 1960s, and other agencies have done so too. But the NOAA measurements are among the best, and these are the results that they show. You can see that between 1990, which is marked here by this arrow, where there was an apparent pause in the heating of the ocean, and the present, where there's now nearly 25 of these units, the ocean has heated by that amount. Now, if you calculate the total amount of heat that the ocean has obtained during that period of time, that 30-year period of time, it's nominally 25 with 22 zeros after the 25 in joules. Now, a joule is about 1/4 of a calorie. So if you're thinking in calories, you can think that way. Now, if you take that number of joules and divide it by the area of the Earth, and you also divide it by the number of seconds there are in 30 years, you get that the ocean has absorbed 1/2 of a watt per square centimeter, calculated on the basis of the entire surface of the Earth, not just the ocean area. So this fact, the fact that the ocean is heated that much, is an absolute proof that the Earth is heating considerably. Now, it's about 4 times less than the IPCC thinks the Earth is heating, but that's because the excess gets re-radiated, and it gets used for other reasons. It gets used to melt ice, and it gets used to heat the land. But the ocean absorbs most of the energy that comes in, and the reason for that is that when the surface of the ocean gets warm, mixing drives the energy below. But when the surface of the Earth gets warm, there isn't any convective mixing. It has to diffuse below, and that's a much slower process than the mixing that can occur in the ocean. Let me go on with a little bit more discussion of this ocean business. The radiative forcing value that the IPCC suggested for 2011 was 2.29 watts per square meter. Now the ocean heating, as we saw, is about 0.5 watt per square meter, and it's known that melting ice and heating land adds a little bit more to that. The difference is 1.71 watts. What happened to that 1.7 watts? Why didn't that 1.7 watts get collected too? Well, the reason is because things heated up. And since they heated up, more radiation was emitted to space because the Earth was warmer. And so one can calculate how much warmer the Earth should be. How much warmer does the Earth have to be to emit an additional 1.7 watts? Well, that's calculated by the so-called Stefan-Boltzmann law. And I have the numbers down here below. If we assume we started out at 61 degrees Fahrenheit, it's going to take 0.9 of a degree Fahrenheit to get the extra 1.7 watts of heating, or 0.6, or 0.5 units if you're measuring them in Kelvin. Now, the temperature data that have been published show an increase since 1990 in Earth's total average temperature of about 0.6 degrees Kelvin or 1.1 degrees Fahrenheit. So you can see it makes sense. The 2.29 watts per square meter is perfectly consistent or nearly consistent with the amount by which the Earth has been measured to be heated. One can say, therefore, that the 2.29 watts per centimeter looks like a pretty good value, even though it is said to be quite uncertain. On the other hand, I would also note that IPCC probably selected 2.29 watts per square centimeter because it was consistent with the amount that the Earth has been measured to have heated. So the question then becomes, how accurate are the measurements of the heating? And I'm not going to get into that. These are, however, the Earth heating results. The surface, if we measure if we measure only since 1980, which is the time that calculation was based upon, because the ocean heating was based on measurements as of 1990, actually. If we look from 1990, the ocean has increased about 0.6 of a degree, and the surface of the Earth has increased by about 2 degrees. Now, the average only comes out to 1 degree because the Earth has a lot more water than land, and you have to take that into account in calculating the average. The last thing that one can point out on the oceans is that, as said earlier, they absorb nearly all the heat, about 93% of the heat. Melting ice only absorbs 2.7%. Those two effects raise sea level in two different ways. First, the heat that's absorbed by the ocean causes it to expand, just like the mercury expands in a thermometer. And since there's an enormous amount of water that is heated, even though the temperature is only a very small fraction of 1 degree, that works out to about a 3.5 centimeter increase in sea level. Now remember that we're talking about 2011 here, not the current date. The melted ice, that 2.7% of the heat, melted about 21 million tons of ice. And that causes a 5.5 centimeter increase. The total is about 9 centimeters or 4 inches as of 2011, according to IPCC, and the science that their results are based on. Now, just think how lucky we are that the ocean absorbs 93% of the heat. If we were melting ice with 93% of the heat, there would not, we'd have an awfully large increase in the level of the sea. Okay, my last subject then is the clouds. And these are cloud measurements that were made between 1980s and 2010 by an organization called the International Satellite Cloud Climatology Project. There were several other cloud studies by other countries and groups, but this is the most complete and most complete both in time and in surface of the Earth. And what they showed was, what this particular study showed was that in the 1980s, between 1980 and 1990, the cloud cover was somewhat larger than it came to later. In fact, it was about 1.5% more than the average for the whole period in the 80s, and it was about 1% less than the average for the whole period after 1995. So that's a 2.5% change from the 66% or around the 66% average that occurred during that period. The question that I wanted to look at was, could that increased cloud cover during the 1980s possibly explain the absence of ocean heating during that period of time? And it turns out that it can and it can't. This is the calculation based upon all the data that I've already presented. The Earth's surface is covered with an average of about 66% clouds. It reflects sunlight. The clouds reflect sunlight, and that amounts to a 50 watts per square centimeter cooling of the Earth. It also reduces the infrared emission because the clouds are colder than the surface, and they emit less light to space than the surface would. And it reduces infrared emission by about 27 watts per square meter. So the net effect of the clouds is that each cloud, or each square meter of Earth, is reduced, is cooled by 23 watts per square meter by the clouds. Now, if you change the 66% by 2.5%, you got to multiply that 23 by 2.5% and divide it by 66. It comes out to 0.87 watts per square meter. That means that in the 1980s, it's possible that the Earth was cooled by the increased clouds by that amount. But the ocean would have stopped heating only if we got rid of that whole 2 to 3 watts per square meter that the IPCC predicted. So I don't think that 2.5% change in clouds can explain the absence of cooling that occurred in the 80s. On the other hand, the IPCC number is very uncertain. And if you took the lower limit of it and then went back as far as the 1980s, when there was quite a bit less carbon dioxide in the atmosphere, only 345 parts per million compared to 410 now. If you went back then, this would not be very different from this. The minimum possible radiative forcing numbers would be comparable to this 2.5% change in clouds. So that's sort of an unexplained phenomena that may or may not. It certainly is ignored for the most part because none of the other investigations of cloud cover were able to confirm the same result that this one study that I've shown has found. And when IPCC talks about this problem, they completely ignore the data that I showed in favor of some less complete data that don't show that effect. So I can come to a few conclusions. One, the measurements of the ocean heating leave no doubt that the Earth is warming. The calculations of radiative forcing, they give a large range of values, so the calculations do need to be improved. But the increase in land and sea temperatures seem to confirm the mid-range values for the radiative forcing. So the IPCC seems to be on the ball. But the standard atmosphere is not adequate, and infrared from the stratosphere will vary greatly with latitude and season, and that's a cooling effect that could be larger or smaller depending on the variations in the stratosphere and troposphere that latitude and season produce. And finally, there's this nice, interesting, unexplained 1980s pause in ocean heating that I'd love to see a scientific explanation for. Well, that's can we switch back to the that's the end of my presentation, and I'd be glad to answer some questions, but I would like to make just one final remark. If you look at the cause, if you look at the cause of global warming, it is very easy to determine that there is absolutely no doubt that we have a problem. Now, when people look at the consequences of global warming, there's lots of argument, especially in the media and amongst the people. They say the weather is hot today and cold tomorrow, so how can we blame all these weather things on global warming? Well, the reason you can blame them on global warming is that we know from understanding the cause of global warming that problem has to be there. So that's the final conclusion that I want to make from having looked at this issue. The analysis of the cause is the most strong proof that there is a problem that has to be dealt with. Thank you.
Thank you, Paul.
Okay,
We'll switch.
we're switching to the
We're
questioner
switching.
now.
Okay, thank you for that, explaining the complexities of understanding CO2 chemistry. We didn't even touch upon the effects of carbon dioxide acidifying the ocean, which absorbs a tremendous amount of the carbon dioxide, as well as absorbing a lot of the heat. And so we have, I wish we had a live audience that we could reproduce the warm applause that Paul received when he first gave this talk. But I have collected questions from that earlier presentation. And so I'm going to give Paul the stage back and I'll ask the questions.
Okay, thank you, Larry. I'll take that as very nice applause all the same.
Do you have any comments about the effect of all that heat absorbed by the ocean on ocean currents?
Yeah, that was an interesting question. You know, the temperature of the ocean doesn't change a whole lot as a result of that heat. It's a fraction of maybe I don't actually know the numbers, but it's in the hundredths or thousandths of a degree. The surface of the ocean does heat somewhat, though. As you could see in that one slide, the surface of the ocean was a fraction of a degree Fahrenheit. Higher than it would otherwise be. I'm not sure that would produce any significant effect. However, the natural currents that do occur move warmer water from the equatorial region to northern latitudes, and the flow at lower depths brings colder water back. So I would say that the currents have a bigger effect in mixing up the heating effect that occurs than vice versa, the heating effect changing the currents. But that's not really an area of my expertise. It's a problem that goes beyond physical chemistry, that's for sure.
The next question has to do with the rise of sea levels. You mentioned ice in two contexts, absorbing energy and rising sea level. The effect of energy absorption affects all ice, but melting affects only ice on land, because when the ice floating on the ocean, when that melts, it's akin to ice in a full glass of water. The ice melts, but you don't spill over the brim because the amount of water displaced is compensated for with the less dense ice melting. So could you comment on that?
Yeah, that's Yeah, I'd have to think a moment about that because uh, it's true, the ice that's floating. Uh, it's true, the ice that's floating would not raise the sea. The reports on sea level rise are somewhat consistent, or rather consistent with the although rather uncertain too, with the numbers that I gave. So that doesn't prove a whole lot. I think that a large fraction of the ice that melts is from land, from glaciers, from Antarctica, from areas of the Greenland and north. I know that there's, however, a large change in sea ice, but sea ice changes considerably from year to year. In fact, I don't recall the exact numbers, but there's a very large decrease in sea ice during the summer that is restored in the winter. And it's the sea ice that changes so much when it gets cold, because the ice on land can only be there because it rained or snowed to produce the ice. But the sea ice can be there because it gets cold and the water freezes. So to some degree, the melting of ice on water is compensated for by the freezing of ice on water from winter to summer and vice versa.
Okay, so our next question has to do with climate deniers. What figures are they using or not using? What are they leaving out? Are they using bad information?
Yeah, well, I think that one of the big problems with people who are called deniers is that it's a problem with the media and with the IPCC in a way. If you read IPCC, there's 4,000 pages and there's almost no information about the cause of global warming. I mean, they'll tell you what the answers are, but they will not explain the details. I had to dig real hard to find out information about the stratospheric effects on emission to space. The media talks only about temperature and hurricanes and all of the other effects that are most alarming that perhaps people can understand. But what they don't talk about, and in fact, IPCC has so much on temperature and so little on energy, and yet it's this enormous amount of energy that has been measured and proven to exist in the ocean that demonstrates that there's one quarter of all the excess energy that IPCC, that the global warming people are predicting, is already there in the ocean. And so I think that well, maybe people can't understand energy, but actually they can. I mean, people pay for energy every day. I mean, you know how much it costs to pay for a few kilowatts of electricity, and to tell people that the ocean already contains 1,000 times more energy than the whole output of the U.S. electrical system you can think that that's a pretty valuable change, because the electrical system energy output is worth an awful lot of money. I think it's just a matter of talking about energy more than temperature and weather effects to convince any denier that there has to be a problem that must be solved.
Well, I hope everyone in our audience takes that to heart, and the next time they have conversations with family and friends, energy will be a big part of the discussion. The next questioner talks about a presentation we recently had by Elizabeth Kolber in her book, Under a White Sky. She recounts numerous schemes to cool the Earth by injecting particles, microdiamonds to sulfur up in the atmosphere. This clearly raises a lot of concerns. Based on your research and analysis, what do you think of the idea, its promise, your concerns about it?
Yeah, well, Culver also talked about various other engineering schemes to deal with problems in the Earth that had backfired. And that's another one that is almost certain to backfire, because it's very difficult to predict the unintended consequences of such a major effect. I don't have any ability to support that kind of an idea at all. The problem is that we burn too much carbon-containing fuel and have to find other ways for generating the energy that we use, generating electricity and heating our homes and running our machines and our automobiles and our trucks. We have to do that with some other form of energy and decrease the amount of carbon that we're emitting. And then this problem will tend to go away over time. I think the best way to go about that is one that's probably politically very difficult. It is to put such a large tax on carbon that people will become much more conservative about using it. And there was a, it wasn't long after the golden age that we started to tax income. Now we've got the carbon age and we should start taxing carbon. So it makes sense to tax the thing that is an excessive problem that's producing excesses in the world. But one of the ideas that has been pushed is that the government should tax carbon producers and carbon importers, tax the amount of carbon that's present in the natural gas, the oil, the coal at the wellhead or the mine, and make that tax very high so that the people that use it are going to have to pay a lot more for the things that that energy does for them if it's derived from carbon. And then return the tax to the people on a per capita basis. So the people that use a huge amount of energy are going to be paying a lot more than they get back, and the people that are efficient in the use of energy will get back a lot more than they spend. But that evidently is politically rather difficult. There's a lot of people in this country, though, that have said they think it's a good idea.
You got to pay for what you use, and I would endorse that. And you and I are probably the only ones that'll fall on our swords.
In fact, I might add that just yesterday at Chautauqua, there was another talk that related to the burning of coal. And it explained the fact that when you burn coal, there are many external costs that are not borne by the people that sold the coal or by the people who burned the coal. Coal causes health problems, and it causes the carbon dioxide problem that we presently have. And it's going to be very expensive to deal. It is very expensive to deal with health problems that coal burning can produce. And it's going to be very expensive to deal with the carbon dioxide in the atmosphere. So the people that are burning the coal or producing the coal are the ones that should be paying for that. That means the prices should reflect the actual costs, not including all of the external costs. That was a subject in yesterday's lecture.
So our next questioner begins with a comment of a way to explain temperature versus energy. He comes from the medical world and talks about a rise in body temperature of 1 degree. We would have a fever and we'd be reluctant to walk around. And a rise of 2 degrees would be seen as medically very serious. That might be another way to talk about it. The main question he has is about latitudes. I was wondering about how radiation or absorption is impacted at different parts of the Earth's emission zones, the poles versus the tropics. Could you say a little bit more? Because it seems that a lot of the impacts are being felt more at the poles. And do the various investigators agree on that issue?
Yeah, I can't say a whole lot about that. I have to think a moment here. Let me just say first, though, that the Earth is developing a fever too. It seems to me, and there's not much doubt that it's creating symptoms, so to speak, that floods, fires, and crop failures, perhaps, or extreme temperatures that didn't otherwise occur so easily. I don't really have something useful to say about the geographical variations. I would say, however, that that there's lots of discussion of that in the IPCC report. I think that the IPCC has wanted to make sure that anybody that says, how is this going to affect us where we live, will be able to look in the report and find that there's something for them.
And I might conclude with a comment. I had done a simple-minded calculation of the weight of the atmosphere, and that's a measurable thing. And how much energy would it take to raise the temperature of the atmosphere 1 or 2 degrees? And it turns out that the energy required is encapsulated in the nuclear arsenals of the United States and perhaps more. And the scary thing of your talk, Paul, is that we're talking about a fraction of the energy, because most of the energy is in the oceans. Mm-hmm. So with that, I'd like to thank Paul once again, and hope everyone watching this video will join me in applause in supporting all your work.
Okay, thank you.